Hello everyone. Let me start with a question. What's the very first thing you probably do in the morning? For most of us, it's brushing our teeth, taking a bath, or washing our face, and all of these activities involve one magical class of substances, soaps and detergents. They may look simple, but chemically, they are powerful cleansing agents that work on a microscopic scale to remove dirt, oil, and grease from almost any surface. Both soaps and detergents belong to a group of compounds called surfactants or surface active agents. These molecules can reduce the surface tension of water, allowing it to mix with oily substances that normally wouldn't dissolve in water. The beauty of their design lies in having two different personalities within the same molecule. One end loves water, and the other hates it but loves oil. This dual nature is what makes cleaning possible. And as you'll see, there's a fascinating chemistry behind it. So, what exactly is a soap from a chemist's point of view? A soap is the sodium or potassium salt of a long chain fatty acid, usually with between 12 and 18 carbon atoms in the chain. Take sodium stearate, for example. Its formula is written as C17H35COONA. That's a 17 carbon chain with 35 hydrogen atoms, a carbon double bonded to oxygen, and then an oxygen atom bonded to sodium. Another common one is potassium oleate, written as C17H33COOK. These soaps are made from fats or oils through a process called saponification. In this reaction, a triglyceride, which is a fat or oil, reacts with sodium hydroxide or potassium hydroxide, producing the soap and another useful product called glycerol. If you could zoom into a soap molecule, you would see a long hydrocarbon tail that hates water, that's the hydrophobic part, and an ionic head that loves water, that's the hydrophilic part. This unique design is the secret behind soap's cleaning power. Let's break down how soap is actually made. In the saponification process, fats or oils are boiled with a concentrated solution of sodium hydroxide or potassium hydroxide. The general reaction can be described as fat or oil, which is a triglyceride, plus sodium hydroxide gives sodium salt of the fatty acid, which is the soap, plus glycerol. If you want a concrete example, one molecule of tristearine, written as C57H110O6, reacts with 3 molecules of sodium hydroxide to form 3 molecules of sodium stearate, C17H35COONA, and 1 molecule of glycerol, C3H8O3. Once this reaction is complete, the soap solidifies upon cooling. It's separated, washed to remove leftover alkali, and then cut into bars or molded into pellets for commercial use. Now comes the magic part. How does soap actually clean? Oil, grease, and most dirt particles are non-polar substances. This means they don't mix with water, which is polar. Soap molecules solve this problem by acting like a bridge. The hydrophobic tail of the soap molecule buries itself into the grease droplet, while the hydrophilic head sticks out into the surrounding water. When you scrub or agitate the surface, these soap molecules surround the droplet, forming a spherical structure called a micelle. Inside the micelle, the grease is trapped in the center, and the outer shell interacts with water, allowing it to be rinsed away. So essentially, soaps take something that water alone can't remove, wrap it up, and make it water soluble so it can be washed away effortlessly. However, there is a catch. Soaps don't work well in hard water. Hard water contains dissolved calcium and magnesium ions. These ions react with the soap to form insoluble salts, which appear as a curdy precipitate called scum. For example, 2 molecules of sodium stearate, written as C17H35COONA, react with 1 calcium ion Ca2 plus to give calcium stearate, written as open bracket C17H35COO close bracket 2Ca, and 2 sodium ions Na plus. This scum not only wastes soap but also clings to fabrics and surfaces, reducing the cleaning efficiency. That's why in hard water regions, people often prefer detergents instead. So, what's the difference with detergents? Detergents are synthetic cleaning agents typically made from petroleum hydrocarbons that are treated with sulfonic acids and then neutralized with sodium hydroxide. A common example is sodium alkyl benzene sulfonate. Like soaps, detergents have a long hydrophobic tail and a hydrophilic head, but here, the head group is a sulfonate ion instead of a carboxylate ion. The key advantage is that detergents do not form insoluble salts with calcium or magnesium ions, so they work equally well in both soft and hard water. They can even function effectively in acidic conditions. Because of this, detergents are widely used in household cleaning products, laundry powders, shampoos, and even industrial degreasers. So, to wrap things up, soaps are biodegradable and eco friendly, but they lose effectiveness in hard water due to scum formation. Detergents are effective in all types of water and under a wider range of conditions, but some types are non biodegradable and can cause environmental pollution. Both soaps and detergents work through the same core mechanism, micelle formation and reduction of water's surface tension, but their chemical differences determine where they are best used. In fact, modern cleaning products often use blends of soaps and detergents to get the best of both worlds, high cleaning power and lower environmental impact. I hope this session has helped you see that every time you wash your hands, clean your clothes, or do the dishes, you are actually applying some very clever chemistry. See you in the next class with another fascinating concept.